Okay, so we're back at that example with 3 restaurants in which we are assuming the probability to some state to move to state new only depends on last state previous. So in other words, the probability of going to Margarita's restaurant, it only depends on when I've been last. I don't have to count the whole history, just the last time. So this number in here, this 0.2, is the probability to get to Margarita from Bertucci, right? And this 0.3 here, this is the probability of moving from the other way. To move from Margarita to Bertucci. So what we do last time, we said, we start with we call this simulation or iteration. We start with a pi 0 distribution of agents or population. That is how many people initially go to each restaurant. So we have here B, M, S, and we have pi 0. That is the initial distribution. Let's just say 1/3, 1/3, 1/3. Doesn't have to be uniform, but typically we start with a uniform distribution. And then how does things move on to the next day? If I want to know how many people, so after one day or iteration, I want to know how many people are going to go to B. And I said pi 1 of B, we did this last time. How do I count how many agents will move to B, or what proportion or probability of them will move to B? I'm going to say, well, how can I come to B? This is day 1. This is day 0. Right, so this is day 0. That's the initial distribution. I'm going to say, well, these are the people that were initially in Bertucci, the previous day, times the probability of going from Bertucci to Bertucci, right? Plus the people who were in Margarita the previous day, times the probability of moving from Bertucci to Margarita, right? Given I've been in, sorry, the other way. So given that I've been in Margarita before, what's the chance to move to Bertucci now? Plus the probability of being in Saro before times probability of Bertucci given Saro. So that's how I say, we did some calculations over there, and we say pi 1, I'm not going to repeat the calculation, that was 0.433, 0.333, and 0.233. But then I can do exactly the same thing for the day 2. So pi 2, next day 2, I'll say, well, what's going to happen with pi 2 of anyone? That's only for 1B. That's the calculation going here, but I could do the same calculation for M and for S. So pi 2 of anyone, we'll say X, any of the 3, is the previous in Bertucci the probability or density in vector G, times the probability transition matrix to move to X from vector G, plus the previous in Margherita times the probability of moving there from Margherita, plus Sato times the probability of moving there, Sato. That is for any X, B, M, and X. So we did that second time, we got 0.473, 0.333, 0.193. Again, applying this equation to the previous round. That's where we were. I can write this equation, instead of writing it this way, I can write it in a vectorial format. I can say any pi t for some round t as a vector, this is a vector notation, is a vector of three things. Is pi t of b, then is pi t of m, and pi t of s. It's three values. It's like an array of three things. And as a vector, pi t plus 1 is the previous pi t, the previous vector, times the matrix P. This matrix. Right? If you look at these equations, they effectively multiplying the previous vector counts or probabilities with the transition matrix, right? How do I multiply a vector of 1, 2, 3 things with the matrix? How does that happen? Or in general, two matrices.
Like you make a linear combination of the columns, like you.
So I take the vector row and I multiply it with a column, right? So to get the new B, I take the previous vector, say 1, 3, 1, 3, 1, 3, and I multiply it with this column. And then to get the new M, I take the previous vector and multiply it with the second column. And to get the S, I get the previous vector and multiply it with the third column. How many people have seen this vector multiplication, matrix multiplication kind of thing? When I take a row from here, multiply with a column from here. That's how matrices multiply, right? Linear algebra. When I have two matrices, or a vector in a matrix, if dimensions, I need the number of columns here to be equal to the number of rows in here to do that. I take a row from the left matrix and multiply with a column for the second matrix, get the value. So in here, when I write this equation, what are the sizes? What's the size of PT, the previous distribution? That's 1 times 3, right? Because I wrote it as 1 row and 3 columns. This matrix is what size? This P matrix. 3 by 3. So if I multiply 1 by 3 times 3 by 3, what do I get? 1 by 3, I get this guy. Okay? So what did we say? If we keep iterating, right? If we keep doing this, that's the iterative method. At some point, this pi of n, which is of course pi of n minus 1 times p as a vector, at some point this will be convergent. That is, when you do this enough times, you're going to notice that the pi values don't change anymore. They kind of converge to a stationary distribution. AKA, they don't change. Then that's the stationary distribution that we usually want to find out in a Markov chain. So we're going to call this, let's call it pi star, the stationary distribution. That is, what's the property of a stationary distribution, the limit of it? What does it mean does not change or convergent? Convergent does not change. So that must have the property, this pi star, that when I multiply with p, when I do pi star times p, right? I do one more round, what happens? I get back pi star, right? That's what it means not to change. But when I do the transition matrix on it again, once I have a stable population of people to Bertucci, Margherita, Saro, once I move it to the next round, the next day, I get the same exact distribution of agents. So that's pi star. Now, this in here, P, it's called a stochastic matrix because each row sum to 1. Right? Each row sums to 1. So one way to find pi star is to do exactly this. Repeat this process and measure the differences. And when you see it doesn't change anymore, that's it. That's your stationary distribution. Another way to find pi star solving equations system. Well, I have pi star time equal pi star plus times p. So if I write that as a system of equations, I get pi star of b is 0.7 pi star of b plus 0.3 pi star of m plus 0.3 pi star of s. Then I get pi star of s is 0.2 and pi star of b plus 0.6 pi star of m plus 0.3 pi star of s, and then pi star, that was m, sorry. Pi star of s is 0.1 pi star of b plus 0.1 pi star of m plus 0.25 pi star. So this is like XYZ, right? It's a system with 3 equations and 3 unknowns. Like if I have to write pi star of b, let's call this x, and let's call this y, let's call this z, I get what? X equal 0.7 x plus 0.3 y plus 0.3 z. Y is 0.2 x plus 0.6 y plus 0.3 z, and z equal 0.1 x plus 0.1 y plus 0.5 z. That's what it is. Now, can I solve this system? 3 equations to 3 unknowns? I cannot. The reason is one equation, it can be obtained from the other 2. If you remember linear algebra from high school, these equations have to be independent to solve this system, or affinely independent, or the determinant of this matrix have to be. What does it mean for 3 equations to be independent? Once I have to reduce it to 0, I have to move this x on this side, this y on this side, and z on this side. I get 0, 0, 0. I do the determinant of that matrix. What needs to happen to that determinant to be able to solve the system? Anybody remembers that? No? We don't remember determinants? When is this system linearly dependent? Okay, we suck at linear algebra. Yes.
Determinant is 0?
Determinant is 0.
Yeah.
So if I get determinant 0, I cannot solve it.
Yeah.
Right? If the determinant is non-zero, I definitely can solve it because this matrix will have an inverse.
Inverse, yes.
So I don't want to go into determinants at all. Yes?
Why the 2x plus 0.6y plus 0.2b?
This?
Yeah.
Is it 0.2 here?
I think so.
Yeah.
Point 25x. So I want to show the dependency without going through the determinants. Okay, we don't need the determinants to show the dependency. I'm going to take those first two equations. So equation 1, equation 2, equation 3. I get equation 1 plus equation 2. What do I get if I sum them up? Equation 1 and 2. X plus y equal, how much do I get if I sum up? 0.9x plus 0.9y, 0.5z. Now what I'm going to do, I'm going to manipulate this, summing up equations 1 and 2. I'm going to get, what happens if I move the 0.9s in here? If I take x, I have a whole x and a whole y minus 0.9x minus 0.9y. So x minus 0.9x plus y minus 0.9y equal 0.5z. That is to say 0.1x plus 0.1y equal 0.5z. Now if I add 0.5z to this, I get what? 0.1x plus 0.1y plus 0.5z equal, how much is 0.5z plus another 0.5z? Isn't that the third equation? This one here is exactly the third equation. So what I showed is that I can take the first two equations, manipulate them a little bit, and get the third one, which means the third equation doesn't give me any additional information. I can obtain the third equation from the first two. Or I could have taken the determinant of the matrix, and if it's 0, and I knew it's going to be 0, means I cannot solve the system. The reason I know it's 0 is because of this. If all row sums to 1, this matrix is singular. Meaning you can solve the equation system if it sums to 1. In fact, if it sums to a constant, all rows sums to the same constant, means the rows are linearly dependent. But how do we solve it? We have another equation that's not part of this system. We know another thing about pi star. What's that other thing that we know about pi star?
That pi b plus pi p plus pi m, or x plus y plus z equals 1.
Correct. Pi is a distribution. That means pi star of b plus pi star of m plus pi star of c must be 1. In my case, that's x plus y plus z equal 1. That's not linearly dependent with those two. So how it works, if you remember linear algebra, I can remove any one of these equations because they are linearly dependent. In here, it's clear that I can remove the third one because the third one I can get from the other two. But you could remove any equation you want because linearly dependence means any one you take out, you can obtain that one from the other two. But we add this one in. So we make a system that are three equations, x plus x equal 0.7x plus 0.3y plus 0.3z. That's equation 1 from here, and the other one is y equal 0.2x plus 0.6y plus 0.2z. Now this is solvable. So I got only two equations from the transition matrix. I don't care about the third one because that one's no new information, but I added this equation in, that pi is a distribution. And now I can solve this system. Solving this system gives me x equal, I can use substitution or something like that. X is 1/2, y is 1/3, and z is 1/6. you should remember how to solve a system of 3 by 3 equations with substitution method, for example. There's also triangulation method, whichever one you like. In computer science, even though it's a math class, we don't put emphasis on solving systems of equation. We think that's pure mathematics, so we fire up MATLAB and say, solve this equation for me, okay? We trust the people in the math department to implement the proper solver in MATLAB. Right? So in general, as computer scientists, unless the problem specifies solve it by hand, we mean, you know, when you take any other courses like machine learning, data mining, you're not gonna solve the system by hand. You're gonna fire up Java, MathWorks, MATLAB, Mathematica, something, whatever you like, put the system in, solve it. If the problem says do iterations or simulations, you gotta do this. But again, I don't know if there's a policy about this, but I would be totally fine if you guys implement, instead of doing it by hand, write a program that says, here's my transition matrix, here's my initial pi 0 vector, multiply with p to get pi 1, right? This is pi 0 times p. This is pi 1 times p. Multiply with p and again with p and again with p until you notice via some epsilon that the differences don't change. There's no difference anymore. And at that point you stop the program and say, that's my stationary distribution. So you get this problem in the homework or not in the homework, it's fine to write the program to do it. In math department, they do it by hand. Okay? So there's two ways to solve this. There is a better way to solve this system. I'm not going to get into it at all. I'm just going to mention it, that due to how geometry works, this vector pi star has to be an eigenvector of this matrix. How many people have heard that name, eigenvector? Very good. So I can't get into that, but if you know linear algebra, that'll be the first course, college level of linear algebra. Due to how it works, has to be an eigenvector. There are faster ways to obtain eigenvectors than by solving the systems. So MATLAB, if you ask, give me the eigenvectors of that matrix, will do it faster than solving the whole system. And a matrix 3 by 3 will have 3 eigenvectors. We know which one we want. Each eigenvector corresponds to an eigen what? Value. And what eigenvalue we're looking for? 1. This is the eigenvector that corresponds to eigenvalue of 1. So you can do it very fast by saying, give me the eigenvector that corresponds to eigenvalue of 1. That eigenvector has to be pi star. So that's this example. How about another example of this stuff? I have weather here. 2 states. I have sunny and rainy. And the probability to stay sunny is 0.9. The probability to stay rainy is 0.5. The probability to move from sunny to rainy, of course, has to be 0.1, because from sunny, I get 0.9 to itself. I'm only left 0.1 to the other one. And from rainy to sunny will be what? 0.5. This is clearly not Boston, right? I mean, that's not how weather works around here. But let's say that's Florida or something.
I can confirm that's not true.
So what is the transition matrix here? P. Sunny, rainy, right? The probability to move from sunny to sunny, 0.9. The probability to move from sunny to rainy, 0.1. 0.5, 0.5. So I can do the same iteration. Here's pi 0, sunny, rainy. 1/2. So I start with the uniform distribution. What's pi 1? For sunny, actually, I have it here not uniform distribution, but we can start with the uniform one. So I get 1/2 times the probability to, that's being sunny, 0.9, right? Plus 1/2 times 0.5 here. And this one is 1/2 times 0.1 times 1/2 times 0.5. So this gives me 0.75, and this gives me 0.3, right? And when I move to pi 2, then this is every day, day 0, day 1, day 2. This would be 0.75, that's the previous day, times the probability to remain sunny.
Wait, is that 0.7?
0.7. Very good. Didn't wake up yet. Plus, what's the probability of being rainy and move to sunny, right? That's 0.5. This one here is 0.7. That's the probability of being sunny and move to rain. That's 0.1. Plus probability of being rainy and stay rainy. That's 0.5. So this in here is, how much is this? 6.3 plus 0.15, 70, divide 0.78, right? And this will be 0.07 plus 15, that's 0.22. I mean, they should add up to 1 anyway. So you can see how this goes. I can repeat the same thing, iterate this until I get to a convergence, or I can write the system, which is pi star has to be pi star times matrix P, that matrix. So that means pi star of sunny has to be pi star of sunny times 0.9 plus pi star of rainy times 0.1. And pi star of rainy has to be pi star of sunny times that's 0.5 here, right? 0.1 plus pi star of rainy times 0.5. I also have that pi star of S plus pi star of R has to be 1. So I pick one of these equations, not both because they're redundant with this, and I solve for pi star. That would be the solving the system as opposed to go into the iteration method. Now the last thing I have to say about Markov chains is that they're not always convergent. This pi star, it's usually convergent. For most practical problems, it is convergent, but theoretically, there are cases when it's not. So we don't want to go into the theory of when it's convergent and when it's not convergent, but I can show you an example where it's not convergent. Question? How many people follow me so far? Okay. So, how about another example? Random walk, up, down. So the states now are how big the states should be? Let me see. The states now, I think I have 5 states here, yeah. And up, we always go with probability P, and down with probability 1 minus P. So in here, if I want to go up, that's probability P. If I want to go down, that's probability 1 minus P. So down is 1 minus P, up is P. Doesn't have to be half and half. Maybe I always go up 70% and down 30%. So this goes down, this goes up, again probability P, down probability 1 minus P. But what happens at the extremes when I'm here? I'm going to say you can't stay in that state. This is one of these things that walks through the maze that you can't stay in that spot. You got to move. So I won't allow probabilities that are stationary. Like in these examples here, we had those probabilities that remains rainy, or the other one that you keep going to Bertucci. In here, we say you got to move. But from this guy, where can I move? Only up, right? So this would be 1. From this guy, you can move up 100%. And from this guy, you have to move down 100%. So let's call these states, I don't know, 1, 2, 3, 4, 5, or A, B, C, D, E. And what happens if I start with an agent in state C? 100%. So that's my initial distributions over A, B, C, D, E. C here, it's 100%. There's 0, 0, 0, 0. Say I always start in here in C. What's happened when I move to the next round? So pi 1. Where can I move from C? I have probability, what probability to be in B? I was in C 100%. So in B I'll be what percent the next day? 15. And what else can I be? I can be in here with probability 1 minus P, right? What's my chance to remain in C?
0.
0. What's my chance to be in A?
0.
What's my chance to be in E?
0.
Now, what happens in the next round? I could be 70% in B and 30% in D. So that's not deterministic anymore. What's my chance now to be in A? How can I get to A day 2? I have to say out of the 70% of the people in B, 70% of them will move to A, right? So the probability here is?
What's that? P.
That's P squared, right?
Same thing.
Can I remain in B?
No.
Is there a chance to be in B? No. Can I be in C?
Yeah.
Yes. I can actually come from 2 ways back to C, right? I could have been in B with probability P and go, if I'm here I have to go down. Or I could have gone down the first round and now I go up. So what's the probability of being to B the first round but then going back to C? P times 1 minus P, right? Go up to B and then down to C. What's the probability of going through the D route?
Yeah, that's the same thing.
The same thing, right? 1 minus P to go to D times P. What's the probability to remain in D here? 0. And the probability to go to E? I have to go down twice. What's the next round? What's the probability to be in A?
0.
0. Because in A, I can only get from B. And if I have nobody in B, nobody will go to A. Right? What's the probability to, similarly, this guy here is also going to be 0. What's the probability now to be in C?
0.
In C, I cannot stay in C because I don't have a itself transition. So I can only come from B or D, but I have nobody in B and D at the current time. So tomorrow, guarantee nobody will go to C because the only way to go to C is to come from here or from here, but there's nothing there. Are we following this? So then that's a 0. Now, what's my chances to arrive to B now? I can come from A with probability what? From A to B. Everybody in A will have to go to B, right? Because from A, you gotta go to B the next round. That's 100%. So everybody here has to go to B. Plus, how many people from here will go to B?
P.
P. So that is 2P, 1 minus P. That was the population times P. And here, similarly, I get all the people from E plus 2P, 1 minus P times 1 minus P. Does this sum, remember this distribution has to sum to 1 all the time. This sums to 1, obviously. This sums to 1. How about this sums to 1? P squared plus 1 minus P squared plus 2P, 1 minus P. Sums to 1. A plus B squared formula. A squared plus B squared plus 2AB. How about this? This sums to 1. Something for you guys to think about.
Yeah.
I think it does. So it should sum to 1. Now you can see how in this, if I keep doing this, I won't get it to converge. There's always going to be zeros around there. My point in here is you can see what happens to the distribution with combinatorics. You're going to need to use binomial formula here to see the general form. I won't go into that. I'm just pointing out that if it has this periodicity property, this is a periodic thing. It's not convergent. Most Markov chains do not have periodic properties. So in natural problems, you can assume most of the time they don't have it. But theoretically, you have to check for some condition like that to be sure that there is a stationary distribution. This in here, no matter how many times you go, there'll be zeros in it. That's not going to converge. Yes.
Is it,
Hold on. Let
So
Daniel.
if you had like a single cell phone, so if you had like A has a 0.01% chance of going back to A, and everything else is the same, will it eventually converge?
Probably all those things that are not described regularly like this, they probably don't have a periodic condition. There's something called ergodicity and some theory how to check that. But yes, if you have enough, not to be stationary, if you have enough arrows between the states, because in here, if I allow some jumping around from A, I break the periodicity property. You have a question?
similar question?
Yeah. So you gotta have something very structural to obtain periodic Markov chains.
Is there any way to tell how long it'll take to converge, or is that just like unknown? Like, could you look at a given
Matrix.
Yeah.
I think you can look at the transition matrix and analyze it a little bit and see how convergent it is. Now, of course, in simulation processes, because that's what convergence means, when you start with a uniform distribution, you converge much faster than you start with a weird distribution. If there is a stationary distribution, doesn't matter how you start. You don't have to start uniform. You're going to get to the same pi star. Because the equation is the same, eventually goes to pi star. But starting with a uniform distribution gets you there fast. All right? The last thing I have to say about this, it's going beyond Markov chains. So Markov chains are those models which are memoryless. Memoryless meaning only the current state matters, like in games. If I'm in this state, what do I do next? It doesn't matter how I got to this state. But what happens if I allow multiple states? Like I'm not only saying so in general, a graphical model and later on, as you advance in you get to the PhD, you're going to get to something called a long short, what's the name? long short memory, something like that. It's how when you type on your phone, how does it make predictions for the next word right away? Right? So if you ever wondered that, most phones now do that, right? So when you start typing, at some point they make a prediction, and they're very accurate with those predictions, right? So this is long short memory models. Long short memory models. They model dependencies. It says the probability of some state is not just the last state. It's the last state and this last state and all of that up to k previous states. So where I go next does not depend only the last state I've been, like in Markov chains. It depends on other things. That's how I can predict a word. I'm not only looking at the previous word you typed. That will be a Markov chain, right? That's the bubbler you have in the homework. The bubbler from the homework predicts a word simply given the word before. What if I include the previous 2 words, or the previous 3 words, of the previous 5 words? It's easy to see how I get a much better chance to predict the next word if I look at the last phrase, right? And if I have access to your history, everything you wrote before. So I want to show you an example of this. We cannot solve these kind of problems here, but if we do it by letters, so your bubbler in the homework is by words. You have a word, probability of seeing that word depends on the previous word. So you get the Markov chain because you only depend on the previous state. But say by letters, if I do them uniformly, so I don't account nothing. I say probability of each letter is 1/26. I'm creating a generative model here. I get things like X, O, F, M, L, space, R, X. You can imagine this is completely unreadable. K, H, R, da, 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 da. Because I'm generating each label with uniform probability. Every time I move on to the next letter, I say draw one at random. So I don't have any dependency. What if I do it with frequencies like in English? So I have no dependencies again, but now the probability of a letter is the actual frequency in English. I'll get some letters much more frequent than others. O, C, or O, H, L, I, R, G. That's an example. M, M, I, T, L, W, I, S, so on and so forth. Still makes no sense. The difference between this and this, I'm generating one letter at a time. But every time I pull a letter, I'm not doing it uniformly. The probability of a letter is not anymore 1/26. It's the actual English probability. The E will be the most frequent, A will be a frequent letter, Z will be very infrequent. How about I do frequency of pairs? Probability of a letter depends on the previous letter. That's a Markov chain here. I'm saying when I generate the next letter, I pay attention to what letter has been generated before. Still makes no sense. But now you can see that letters are following each other in a way that matches English, pairs of letters. you know, I is likely to come after T and Y, S after Y and so on and so forth. Why previous I didn't have such a constraint because now every time I'm generating a letter, I'm not just looking at its frequency, I'm paying attention to what the previous letter was. So I know after an R, it's likely to come an E in English and not a Z. So I won't see RZ because that's a 0 probability. Z never comes after R in English. How many people with me for what I'm doing here? Next round, how about if I do a letter based on the previous 2 letters? That's not a Markov chain anymore by letters because I'm not memoryless here, right? Now I'm depending on the previous 2 letters, which is not a Markov chain anymore. So now I get stuff that looks more like English. Still not English, but what happens if I jump into words? Probability of a word. Actually, no, let's do another one with letters. Probability of a letter depends on previous 3 letters. So that way, I'm even more close to English. When I generate a letter, I look at the previous 3 letters to see what's likely to come. This almost sounds like words. Makes no sense. But because every letter has been generated given the previous 3, there's a pretty good chance that that letter will make sense. Because in English, once I see R-A-T, the very likely next letter is E, right? And so on and so forth. Now, not all the words make sense. But you can see how doing it with stronger dependencies, the more you build stronger dependencies, the more you generate text. People have gone very far with this by words. That's like your bubbler. And they generated entire pieces of text that at the first glance, if you don't pay attention, they looks like actually somebody wrote it. In fact, some people at MIT generated an entire academic paper randomly with their computer, and the paper got accepted. They wanted to prove that the conference is useless. So they sent this paper, generated entirely by a generative process, with very strong dependencies. And because the reviewing was so superficial, in fact, the reviewers not even look at the papers in that conference. It's a conference designed to just send people to vacations in fancy places. They don't care about academic value, right? One of the crappy conferences. They accepted it, and then they wrote an article. Hey, I generated a paper completely at random, 8 pages of nothing, and this conference accepted it.
Did they read the paper before they sent it?
What?
Did they read the paper?
I'm not sure.
It's
But
possible the computer made a breakthrough and they didn't notice.
I doubt it. So generating stuff this way, you can get quite far. But of course, to do this, what do I need? If the deeper I want to go into these models, what's necessary? So in here, I don't need anything, right? I generate all letters uniform, that's easy. The information I need to give to my system is just uniform body. But once I go down and down, what do I have to give to my system to be able to do this? Yes?
A sample of correct.
I can give it a sample, but the purpose of the sample would be what? To estimate those probabilities, right? So how many probabilities are here to estimate? When I say I want to know the probability of a letter given the previous 3, how many probabilities are we talking about?
26, 3.
To the 4th, right? Every 3 and the one that's given. This joint is a big joint. That's a huge table of probabilities. And I need a lot of text, a lot of big sample. I need probably all the books in the world to estimate that correctly. So while this is more generatively correct, it generates more proper text, the input in it, all these conditionals, it's a huge input. In here, the input is nothing, right? So the down you go, the more input and probabilities you have to give to the system. That's why those phones get so much better at predicting your word or understanding your voice once you do a lot of talking and texting, because they learn from what you text. The more you type, the better it's gonna know what the next word is for you. It may not be the same for me because maybe I write differently than you. But that's why now most Android and iPhones, they learn from what you type or for what you speak, if you speak to them and make corrections, and eventually they will understand you. So if you have a hard time talking to Siri like it never understands you, persist. Because if you keep doing it, eventually it's going to understand what you say. Even if you don't speak proper English, it's going to understand what you say. All right. So that's Markov chains. And that's all we have to do about probabilities. So we need to move on to the next chapter. Next chapter, what we're going to talk about first is a little bit of search. So search and sorting, what I'm doing now, it's getting much closer to computer science than the rest of the course. So a lot of it was math with some implication to computer science. Search and sorting is actually computer science, 100%. But of course, we're going to talk about it for about a day, and next week we go back to math. Okay. So I have a book of N pages. I'm looking for something. Certain description, chapter, paragraph. Looking for something. So I have three options here. I can do linear search. There's more options than that, but we're going to do three, which is go through pages one by one. I can do chunk search. Examine a chunk of, say, X pages at a time. Just to determine in what chapter or what chunk what I'm looking for is. But then I have to linear search. This will give me the right chunk. And then linear search in that chunk. So I could say, here's my book. I'm going to examine a chapter at a time. I'm going to look at this chapter. Is the character I'm looking for in that chapter? No, it's not. Move on to the next chapter. That's a chunk. And then move on to the next chapter, so on and so forth. So I quickly check to see what chapter contains that character. Say I know it's a story, it's a novel, and I know it's not in the chapter, not in the chapter. I find the chapter. But then once I find the chapter, I need to go through all those pages to actually find where that paragraph I'm looking for is. Right? Or I can do binary search. Binary search is split in half. In that sense, it's the same like a chunk. I split into two chunks. Decide which one to search, which half should I say, and then repeat until size very small. So I'm sure you have heard of binary search. I have a book of 300 pages. I split it in half, and I say the character I'm looking for or the paragraph I'm looking for is in the first half or the second half. Once I make that decision, my book has shrunk in half now. So I'm now looking in the first half. I say I repeat the process. I have 150 pages. Which side should I look at? The first 75 pages or the last 75 pages? Once I decide which side is what I'm looking for, boom, I split it again in half. Until I end up to like something very small, like 1 or 2 pages, and I can just quickly check in those pages what I'm looking for. So we want an algorithmic analysis. And you're going to hear this a lot during your 4 years in here. You're going to hear a lot this term, algorithmic analysis. And if you continue master's, PhD, so on and so forth, you're going to hear it even more. Okay? What this means, I want, roughly, this is very informal. So formally, when you take algorithms, you're going to do this formally. Informally, you want how the running time depends of the input. Actually, the size of the input. So everybody understands that whatever algorithm I have, whether it's a search or some other thing, if I give it a bigger book, it's going to take more time to search it, right? Whether it's linear search or chunk search or binary search, or say I'm doing some fancy thing, of course if I give it a bigger problem, like a bigger matrix or bigger array or bigger book, it's going to take more time. Any algorithm will take more time with a bigger input. So when you ask what algorithm is faster, you mean on the same input, because an algorithm could be very fast on a small book, while algorithm is slower on a bigger book. That's not comparing apples to apples, right? So when we talk about runtime, we always have the size of the input in mind. What's the size of my input here? My book. What's the size of it? Number of pages, right? So in this case, the runtime will be measured as a function t. This is the runtime function. For some reason, everybody calls it t. Of n pages. But if I run an algorithm over students, or over houses, or over a big graph, or if I'm Facebook, it depends what kind of size of the graph I pick on to run my algorithm, right? So you always want to do something size-based when you measure runtime. So how do we think of those things? There's another thing that we need to have in mind. There's always a best case, lucky, an average case, which is more like expected, or a worst case, unlucky. Right, imagine my problem here. I do linear search, right? I go to the pages one by one from the beginning of the book. I'm looking for this character, Jack Sparrow, in the book. What would be the lucky case?
First two.
It's in the first page, right? If what I'm looking for is in the first page, I just stop right there, right? But what's the unlucky case? I'm looking for the same Jack Sparrow, and I'm looking through this book. What's the unlucky case now? It's on the last thing, right? So I have to go to the whole book to get there, right? So if I do linear search, let's say linear search, what is the best case? Runtime. So this is a runtime analysis, best case, worst case, average case. If I do linear search, What's my best case? How many searches or operations I have to do in the best case? One. And that corresponds to what? First page found. What's my worst case? N, right? That is the last page found. On average, how do I think of average? What does that mean? I have to search not one book, but I have to search a billion books. For some books, it's going to be on the first page. For some books, it's going to be on the last page. For some books, it's going to be on the second page, or third page, or fifth page, or middle, or down, or who knows. Let's assume every page is equally likely, right? I'm looking for something, and it's equally likely to be on the first page, or the second page, or any other page. So the probability of found is what, if I assume uniform? Found page is 1 over n. Right? The probability on any page to find what I'm looking for, it's uniform. So then the average is the expected value, right? How do I compute the average here? If it's equally likely to be on page 1 and page 2 and page 3 all the way to page n, what is the answer for the average case? Think about expected values. How do you measure expected values? It's the sum of the value times probability. So what would that be? The expected value would be sum over all possibilities. That was all the values from 1 to n. It could be on any page of v times the probability, 1 over n, right? Because each page is equally uniform. That is 1 plus 2 plus 3 plus n divided by n. It's approximatively n by 2, right? If I do this, it's about half. On average, it's about halfway through. So if you go through a billion books, all of size 200, on average, you're going to search about 100 pages per book. Assuming what you're looking for, it's equally likely to be anywhere in the book. Because of course, if what you're looking for, you look for the author, it's always on the first page. Right? How many people follow me here? Good. All right. There's another thing. When we do the runtime, we care about something that is new, order of magnitude. For reasons that you're going to get into while you are a student here, but not today, it's hard to measure the exact clock time of operations. How many CPU cycles I'm taking. So when we look at those answers, we look more like the order of magnitude. Because depends how you implement this to the computer, depends how fast CPU is, depends on all kinds of things, what data structures you're using. So then we're going to say, what's the order of magnitude here? As an order, that's a constant. Right? 1. And if it be 2 or 3, we'll still have the same order, which is a constant. What's the order here? Order is here is linear or n. And what's the order here? Also linear or n. Even though this is n by 2, this is faster than this, right? The order of it, the magnitude as a polynomial, it's still a linear function in n. How about chunk search? What happens with chunk search? Can I be lucky with chunk search? So how does this work? When I determine the right chunk, I have to do a linear search in that chunk. So what does it mean to be lucky in chunk search? Yes?
The thing you want is in the first page, the first chunk.
First page in the first chunk. In that case, how many operations do I do for finding the chunk? 1 and 1 for finding the page. So that is 2, right? because I have to find the chunk first. I'm lucky, it's the first chunk I'm looking for. In that chunk, now I have to look for Jack Sparrow, is the first page. How about in here? How many chunks are there by the time? If I have X pages at the time, that implies how many chunks to look for? If I divide the book into X pages at a time, how many chunks are there?
N over X.
N over X.
Which you have to read.
So if I'm in the worst case, how many chunks I have to go through to find the right chunk? I'm unlucky, I have to go through all chunks, there's no escape. How many chunks I have to go through? All of them, right? Which is how many? N over X chunks. And then once is the last chunk, I'm also unlucky in finding Jack Sparrow in that chunk. How many pages I have to go through that chunk to find all pages? How many pages are in the chunk? X. So the total is N by X plus X here. Yes?
How do you determine which is the proper chunk width without going through all the pages in the chunk?
Right. So in this story that I'm saying here with the book, it's assuming that you are familiar with the story, and if you see the chapter or the chunk, you immediately know that's not about Jack Sparrow, that's about Jack Sparrow. When we instantiate this with real numbers, it's going to come down to, I have a sequence of sorted numbers, right? And a chunk is from 10 to 20, some numbers. And you're going to know immediately if the number you're looking for is there or not, because you don't have to go through, right? You know the number I have is between 10 and 20 or not. If it's not, I move on. This is just a beautiful story. Relevant question. This assumes that finding the right chunk is a one-time operation. I only need 1 second to determine what I'm looking for is in the chunk or not. If this is not the case, then finding the chunk takes more than one operation. How about on average? How many chunks on average I have to go through? I'm looking through chunks. I'm looking by N over X, the number of chunks, divide by 2 on average. And in the chunk I found, how many pages I have to go through on average to find what I'm looking for? X by 2. By the same reasoning. Right? Now, notice that this as order of magnitude is the same as that. So it's faster, it's divided by 2, but it's not a different kind of function. So, let's focus on worst case analysis. That's what usually people mean. Usually analysis means worst case analysis. Why do I care about worst case analysis more than other things? When I'm really working on a problem, usually I'm Google. And I say, I want the worst case analysis. Why do I want that? If I'm your manager, you work for me, you come up with a solution to, place the ads better. And it's an algorithm. And I'm saying, what's the worst case analysis?
Because odds are the worst case is going to come up, and you have to make sure that it'll happen fast enough.
No. But that's a good answer about the odds. That has to do more with the average case of the odds.
Yeah, I'm saying most likely the worst case will come up. So if the worst case scenario takes.
Yeah, but why do I care about worst case so much? That's my
You
question.
need to fit within a time limit of whatever, based on whatever.
Your answer is relevant to this. It's saying, on average, if I run that algorithm you give me, that solution, 1,000,000 times a day,
Yeah.
which time I care about?
But you only care
The
about
average
one.
case. But the worst case, where's the worst case relevant? It provides what?
It absolutely has to be a certain speed. And
All the time.
the worst case will be-
It provides a guarantee. It says, in the worst case, even if that happens 1 in 100 days, right? Very rarely, I can guarantee that my ad placement or whatever the problem was will never take more than 0.5 seconds. That's in the worst case. So that provides a guarantee that no matter what, no matter how worse things are, it will never be slower than that. So in practice, we care about 2 things. The worst case, which is exactly that. Even if it's very rare, what's the lowest of the lowest difficulty that I can have? Like how much it's going to take. And the average case, it's an operation that runs so many times that as a resource, as how much computation time takes overall, or how much hard drive space, or how much memory, I care about the average case because that's something I'm going to run a lot of times. So let's focus on worst case analysis. Linear search has Tn of n. Chunk search has the running time, we say n by x plus x. Right? And binary search. What's the time for binary search? If I do this repeated division, how many operations do I need to do to get it done?
Log 2.
Log base 2n, but do we know why?
Well, I guess it depends on what you're searching, but like log.
Anything I'm searching, doesn't matter what it's, I have this book of 200 pages.
It halves it, so it's how many halves you need, like how many halving times you need to get to whatever it is you're looking for.
This is my book, right? How many pages it has? 200. After one round of binary search, round 1, what happens to my book in binary search? I divide it in half, right? So at round 1, what's the size of my book now?
100.
It's 100, right? What happens when I divide this in half again? It's only 50, right? What happens when I divide it in half again? 25. So the question is, how many divisions in half I need to do before I'm only on one page, and then I can just check the page. So how many divisions in half? After k divisions, size of the book to search is what? After one division is, we know this is n by 2, right? This is n by 4, and this is n by 8. So after one division is n by 2. After two divisions, n by 4. So after k division, the size of the book will be what? After I do binary search k times, what's my effective size of the book to search?
N over 2 to the k.
That's going to come up a lot. Again, I don't know what this k is. Now I want, we say we want k such that n over 2 to the k, that book that I'm searching, it's only one page. Right? Because that's the point where there's no point dividing anymore the book in half. If it's only one page, I just look for the page. So what's k to have that size? If I want n divided by 2k to be 1, k has to be logarithm base 2 of n. That's how many steps I need to do in binary search to end up with a book that's one page. And then I just look for what I need to do in that page. How many people follow me? If I do binary search will come up in all the courses you take from now on. Okay? Some form of another. And binary search trees also will come up a lot. So if I divide in half, I need to know, that's relevant to his question, you need to know which have to go immediately. Right? Like the numbers, if my numbers are sorted, it's from 1 to 1,000,000, I divide in half my array, now I know where the half is. And I can compare the value I need to look for to the extremes, and I know it's in this half on this half right away. Then I divide in 2 again, and in 2 again, and 2 again. How many times I need to divide by 2 so I get a trivial amount to search? Logarithm. So this in here is log, the running time, T of n, is log base 2 of n. One more thing for chunk search. In chunk search, we have an option. What's the option? When we do chunk search, it's up to us to pick something. What?
Size of the chunk.
Size of the chunk, which is who?
X.
X. And how do we can pick the size of the chunk related to the input, right? We don't have to use the same chunk. If the book has 100 pages, maybe I want a chunk of size 5 or 10. But if a book has 1,000,000 pages, maybe I pick a chunk of size 5,000. It's up to me, right, to decide the chunk. So what is the best X? How do I choose an X? What do I want to do with this T of n? What's my purpose in life here with T of n? I want T of n to be small. Right? Is the running time. Now, I can't get it down to 0 because I have to do a search through n pages. If n is 1,000,000, there's nothing I can do. But I can pick an X. Some X's will be better than others, right? Effectively, what I'm asking here, if n is fixed, n is 1,000,000, or n is 1,000, or n is 300, how do you pick the best X to minimize this value? How do we, if I give you this function, n by x plus x, I tell you n is a constant, you have to choose x to minimize this. What do? Somebody else. You do trial and error until you get a minimum? No. Yes.
Take the derivative and find the minimum.
Okay, and what's the minimum if you do that? This is as a function of x with n constant. How does this look? It looks like this, right? So there's an x that's best x. Turns out if you take the derivatives and all that, best x is the square root of n. So what happens if I put n in here instead of x? What do I get? If I do chunks of size n, how much is this function? n plus 1. What happens if x is 1? How much is this function? But if I do the best x that's square root of n, how much is this function? That's the optimal chunk for chunk search, to pick an x that's square root of n. So if n is 1,000,000, what's the best chunk size? 1,000. What happens if n is 100? What's the best chunk size? If n is 100, 10. So what happens when n is 1,000? How does these three methods play out? This is 1,000, 10 to the third, right? How about 2 square root of n? How much is square root of 1,000? Roughly. We care about approximations. There's no decimals in here. What's roughly the square root of 1,000? 32 point something, right? So this would be approximately 64 because it's 2 times. So 2 times square root of 1,000 is approximately 64. This is 1,000. Let me write it down this way. And how much is binary search? That's a log of 1,000 in base 10. That's approximately what? Again, we don't care about decimals. Yes. 10. Because log base 2 of 1,000, 1,024 would be 10, right? So what do we see? If you do an intelligent search, you do it 100 times faster than a dummy search. How about when n is 1,000,000? How much is the linear search? 1,000,000 because the runtime is 1,000,000. How much is the 2 square root of n, the chunk search? 2,000. And how much is the binary search? 2 log base 2 of 1,000,000 is how much?
20 something.
About 20. Because log of 1,000,000, we know that log of 1,000,000 is log of 1,000 plus log of 1,000, right? We know that log of a product is the sum of two logs. So now if log of 1,000 is 10, log of 1,000 plus log of 1,000 is about 20. Now, how much faster this is? This is 50,000 times faster. So the typical difference between a computer scientist and a smart person, which is not a computer scientist, I'm not kidding now, okay? Don't laugh. Okay? Is to say, what does it matter? Like I have a super fast computer, right? Like I bought the latest Mac Pro, it cost me $9,000. Even if I do linear search, it's gonna be pretty fast. That's how you know this person is not a computer scientist. But there's smart people who think like that. I mean, it's a matter of education to know that. It's, you know, if you do this on the fastest supercomputer, I actually have it written down here. There is an Oak Ridge National Lab computer which has like 17.6 petaflops CPUs. This will still be slower than a binary search on my laptop. Okay? Even though that computer is an entire building of processors. You see my point? The algorithms do matter. It is true that the National Oak Ridge Laboratory has a computer that is 3,000 times faster than my laptop. That is true. But that's not enough to compensate for the fact that this algorithm is 50,000 times faster than the other algorithm. So, this is not to say that you don't want the best hardware. Of course you do. You want the best hardware. But that's an orthogonal problem to having the right algorithm. Even if you are Apple or Facebook and you have a farm of computers at your disposal, or Google, they have a much bigger farm than Apple, right? Google still wants the best algorithm, even though they have infinite computation. Things will still run 50,000 times faster, even if you have a farm of computers at your disposal. So even if you have this computation, you're still looking for computer scientists who do the right algorithm. And when you study more computer science, when you study theory of computation, for example, there'll be some problems for which if you do the wrong thing, becomes unsolvable. Like it's not even a million. It's like you're never gonna get to the right answer, like forever, okay? So there's some problems that you're gonna study. They're gonna be either you do something intelligent or you're never gonna finish. Okay, let's move into sorting. Just to give you guys a flavor of what's going to come in your algorithm course. Sorting numbers, that's what I mean. I give this array. This is an array notation, by the way. 6, 3, 7, 2, 4, 8, 1, 5. Inside the array, I put values. That's the input. Input and input size is the size of the array. In my case, the input size is 8. If I want to write down positions, I do positions on top of the array, like 1, 2, 3, 4, 5, 6, 7, 8. Most people initially, as an undergraduate level, confuse positions with values. Whose 3? Is the position 3 in the array or the value in the position 3, which is 17? Okay? So you got to be very clear when you start computer science, which is today. Are you talking about positions or values? And arrays are different than lists. In an array, it's a continuous chunk of memory I can get immediately into position 4. I don't have to traverse the array because I know where it starts and I know how it's organized. So if it starts at this memory index, if I want position 4, I know exactly where in memory to go to read position 4. In a list, if I give you a sequence, the only way to get to position 4 is to go hoop over the list little by little, to get to that spot number 4. Arrays have this very nice random access. I can access A of 4 or A of anything in constant time. In a list, I don't have this ability to access a position in the list right away. I have to traverse the list.
Are we saying these are 0 indexed or starting at 1?
That's up to you. In theory, when we talk about it on the board, we can start from 0, from 1, whatever is convenient. It's all conceptual. When you implement arrays, depends on the programming language. That's another big mistake people do. They start from 0 when the programming language does not allow 0, like MATLAB. MATLAB always starts from 1. Or they start from 1 when in C++, where the index is 0. When you implement stuff in a programming language, you have to know where the indexing starts. Okay? But not all languages start from 0. Not all languages start from 1. Also, when we do conceptual stuff, we have to be clear where we start, but we can choose our index whatever we like. Like for that purpose, we can start from -5 to +3. That'll be the same. Okay? Now, I want to show you 3 sorting methods. So, obviously, sorting means sorting in order, right? That's what I want to do here. Insertion sort. Here's how it goes. I have this spot. This is my array. I read the first value, 6. I put it in. Right? And then I read the next value. So this is first value. I read the next value is what? I read it from the input. This is the input. This is the output. This is input. Next value is a 3, right? You know what insertion sort does? It's what card players do when they pick the cards one by one. They pick 3 cards, and they always have the sorted. They pick the next card. They figure out where that card goes. So insertion sort, as soon as you pick the next value, puts it in the right spot. So I'm saying, can I put the 3 in here? That's where I put it initially. But then, is in the right position? It has to move. So I move it over, and I get what? 3, 6. Right? Then I read another value. So let's draw this down. Sorry. So I have 3, 6 now. I read another value, that's a 7. Is 7 in the right spot?
Yes.
How do I check this right spot? What do I have to check to say I'm in the right spot? How do I, assuming this was already sorted, how do I know 7 is the right spot? I compare with the previous value, and if it's bigger or equal, it's good. Right? So I know it's in the right spot because 7 is bigger than 6. This is wrong spot because 3 is smaller than 6. What's the next value? 3, 6, 7. What's the next value? I read a 2, right? Is 2 in the right spot? No. No. So if it's not in the right spot, I move 2 over the 7, I swap. Is 2 now in the right spot? How do I know?
6 is smaller.
I compare with 6. So that's again now another swap. So I get 3, 2, 6, 7. And is that now 2 is in the right spot? Are you guys following me? Hands up. So I have to swap again, right? Because 2 is not in the right spot. So I get what? 2, 3, 6, 7. Is that good now? Good. What's the next value that I'm reading? 2, 3, 6, 7. That's what I have so far. Next value that I'm reading is 4. Is 4 in the right spot? Swap. So I get 2, 3, 6, 4, 7. Is now 4 in the right spot? No, I need another swap. So I'm going to get 2, 3, what? 4, 6, 7. Is that now 4 in the right spot?
Yes.
Because it's bigger than the 3. I always check against the left value. If it's bigger than that value, means I'm in the right spot. That's something for you to think about. Is it enough to always check the value on the left? If this 4 is bigger than the 3, I'm good. I don't need to do anything else because everything else got to be in sorted order. So what's the next value? I read an 8 now. That's the new value. Is 8 in the right spot?
Yes.
Yes. Good. So what's the next value? 1. 1 have to be swapped. Here, 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 here. I have to do how many swaps? A lot of swaps. Because 1 has to go all the way to the first spot. So in insertion sort, what is the worst case? Somebody else.
That your input is like sorted backwards, so everyone has to move.
So for the first value, so value ID, position, not value. How many swaps do I need to make? For the first position, when I put the first guy in, how many swaps I make there? 0, right? For the first one, I do 0 swaps. But if I'm in a worst case, when I put the second value in, how many swaps do I need to do? 1 swap. When I put the next value in, how many swaps do I need to do? 2 swaps. What he said is if the arrays is perfectly reversed, the worst case, it's something like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. In that case, I don't do swaps for 10, but 9 has to do swap once, 8 has to swap twice, 7 has to swap 3 times, right? And when I get to the last value, I get n minus 1 swaps. Everybody has to swap all the way to the front. So what's my runtime? 1 plus 2 plus all the way to n minus 1, number of swaps. So how much is that? You guys know that formula? That's what we're going to do Tuesday. How to compute this kind of formula, summations and all that. This is easy to tell. It's n by minus 1 by 2. People have seen this stuff before, this formula here? No? Well, to get n minus 1 by 2, I can put it under the other way, n minus 1, n minus 2, n minus 3, so on and so forth. I sum it term by term. I get n terms. N minus 1 terms all sum up to n, so that's by 2. Next week, Tuesday in class, we're going to prove this formula. So, the order of this insertion sort, if I look at it by the degree of the polynomial, I ignore the 2's and the 1. What's the order?
N squared.
N squared. How about selection sort? Selection doesn't go like insertion. Selection goes like find the minimum. That's output of 1. You set it up right there. Find the minimum, you put the first values and the minimum spot. Then it says find, in my case, what's the minimum in that array? Minimum value? 1. So that minimum for me will be 1. Find the next minimum, meaning not including that one. That's the output of 2. So what's the next minimum? Excluding the one that I already choose. 2. So I put the 2 here. And keep going. What's the next minimum? 3. That's right here. The next value, right? So the next minimum is output of 3. That's 3. That's next minimum. 4. What's the next minimum? What's the next minimum? There's a 6 in there? Is that gonna work? Is that gonna give me the array sorted? If I find the minimum out of the unselected elements, find minimum, next minimum from unselected values. How long is gonna take, worst case? Worst case, how long is gonna take me to find that minimum? The first round. Yes. N. In fact, it's not worst case. It will take n for sure. To guarantee the minimum, I have to go through all the elements, right? Right? So first round, n. Second round, how many finds will take to find the minimum? N minus 1, right? Because now I have only n minus 1 elements. One of them has been selected, right? Remaining. If I keep doing this, I do all minimums, the last one will take 1 step, right? So the runtime will be the same as in there, like 1 plus 2 plus, that's all the way to n. So that's n times n plus 1 by 2. The order of this is also n squared. How many people follow me here? Pick the minimum, that's the first. Pick the next minimum, that's the second. Pick the sub minimum. One more. We're not going to finish it today. But we'll take a minute to start it. This is merge sort. Split in half. That is, if I split in half this array, what do I get? What are the halves? 6, 3, 7, 2 versus 4, 8, 1, 5, right? Let's call this A from the beginning to end by 2. That's the first half. And this is the other half, end by 2 plus 1, all the way to the end. So I split the array in halves. Sort the halves. So I do merge sort of each half. This is a recursive call. Merge sort the first half. And then merge sort the second half. And then combine them. The halves. Turns out that if the two arrays are sorted, when I sort the first half, what do I get? 2, 3, 6, 7. When I sort the second half, what do I get?
1, 4, 5, 8.
1, 4, 5, 8. Turns out I can combine them really quick. If the two halves are sorted, it's easy to combine them. Because I go from the beginning, choose the minimum, and keep going. This is an n time operation. So how do I think of the running time of merge sort? It's a recursive call. So I have to search, I have to sort the halves. This is the sort of size n. This is the sort of size n by 2, right? I have to sort the halves. And then I have to do the combination, which will take me linear time. Now, anybody knows how much is this? If I have a formula, this is not an explicit formula like before. It's a recursive formula. That's your homework for next time. if a function acts like this, it's not an explicit formula. Before you see I got an exact formula. This is a recursion. How do I know how big is it? It's like n squared. If I plug in n squared here, do you think n squared works like that? How much is n squared? Is n squared 2 times n squared by 2 plus n? No. So how do I know what function t satisfies this equation? That's what we need to do on Tuesday. What section is he in? Which one? Doesn't matter. I'll give Priyanka to look at it.